Well, hi everybody, and welcome again to my channel Art and Physics. This video is the continuation of the video on which we use Lagrangian dynamics in order to find the equations of motion of a mechanical system, the part 1. And well, first of all, I would like to apologize for the delay between these two videos. I had a cold, nothing too serious, but I cannot speak very well. So, well, now I'm feeling better. So let's continue with this second part. And well, another important thing that I like to mention is if you haven't seen yet the part 1, I strongly suggest you to do so, because on that part we obtain the expression for the Lagrangian and well the expression for the kinetic and potential energy. Those results will be used here. So if you like to understand well this video, I suggest you to check it out, the first part. So on the screen is again show the mechanical system. The mechanical system, which is formed by these two objects, the card and the hanging mass, and also is shown the Lagrangian equations. And here below is the expression for kinetic and potential energies. So we need to find the two remaining equations of motion, which are the equations associated with the theta coordinate and the u coordinate. So let's begin with theta coordinate. We need to first find the expression for the partial derivative of the Lagrangian with respect to theta dot. So if we if we look closely to the expression of kinetic and potential, we can note that the theta dot terms only appears in the kinetic energy. It cannot appear on the potential, because potential energy do not depend on velocities. So if we took this partial derivative, we can obtain the following results. First, m times L plus u square theta dot, and the second terms came from the term in the big parenthesis, which is equal to n ml plus u x dot cosine of theta. Okay, we now should calculate the total derivative with respect to time of this later partial derivative, the partial derivative of the Lagrangian with respect to theta dot. And let's begin with this first term. I will use a product rule. This will be my first term in light green here, and in light blue I will use this other one, like so. So the derivative of this first green one is 2 m L plus u times u dot by chain rule times the blue function, and now plus green times derivative of blue, which will be equal to m L plus u squared theta double dot. And this second term is slightly bit more complicated, because as you can note, this is equal to the triple product of functions of time. I will name that one as the blue function, and this other two will be the red one. So let's begin with the derivative of the blue function, which is equal to m u dot and times the red one x dot cosine of theta, and now plus, I will continue here below, the blue function times the derivative of the red one, which is equal to, again, product rule, x double dot cosine of theta, and now minus x dot times theta dot times sine of theta. Where does it come from, this later expression? Because the derivative of cosine is minus sine, and we should remember that theta is also a function of time, so we apply the chain rule. Okay, perfect. We now shall find the partial derivative of the Lagrangian with respect to theta. And if we look again the expression for both kinetic and potential, we can note that theta appears and actually in both of these expressions, and also both in kinetic and potential. So we have to be a little bit more careful here, but we apply the same rules. The partial derivative with respect to theta will lead us to the following result. First, in kinetic energy will appear this one, minus x dot L plus u theta dot sine of theta plus mx dot u dot cosine of theta. And now in the potential energy, we should be very careful here because it's easily to get lost in the sign, the minus signs here. Cosine of theta appears in potential energy with a minus sign, but Lagrangian is kinetic minus potential. So, and derivative of cosine is minus sign, so it's a little bit cumbersome, but well, you have to be careful, no more than that. So we have here minus mg L plus u sine of theta. And with this result, we are ready to set up our second equation of motion, which is just simply this first total derivative minus the partial derivative of Lagrangian with respect to theta. So we will obtain the following. I will write all this expression here. It's a little bit long, but well, let's do it. Plus ml plus u squared theta 2 dot plus mu dot x dot cosine of theta plus ml plus u. I will multiply all the terms here in this big parenthesis. x2 dot cosine of theta minus ml plus u x dot theta dot sine of theta, and now minus this second partial derivative. We will lead to plus mx dot. Let's write it as solo ml plus u x dot. It will be much easy to see the similar terms. Sine of theta minus mu dot x dot cosine of theta plus mg L plus u sine of theta. All of these expressions are equal to 0. Why 0? Because in this problem we are assuming that there is no non-conservative forces present. So nothing like a viscous force or frictional force or nothing similar to that. So if we look this final expression, we can note that some terms will cancel out. First term we will cancel out with this by this another one, and also this with this cancel each other. So the equation of motion, the second equation of motion, will be as follows. I will write first the terms associated with second derivatives. Good. It's convenient to do so. Plus L plus u x2 dot cosine of theta. These are the two terms with second derivatives, and again, and now times 2m L plus u dot theta dot, and finally plus mg L plus u sine of theta equals to 0. That's it. This is the second equation of motion. I will draw here a big red rectangle. Perfect. Last, the third equation associated with the u coordinate. The process is very similar. We will find again the partial derivative of the Lagrangian, but now with respect to u dot. Looking again to the expression of kinetic and potential, u dot only appears on kinetic by the same reason that I that I mentioned before. In this case, this will be this partial derivative, and the total derivative of this later partial derivative will lead us to the following result: m times u double dot, again here product rule, times x 2 dot sine of theta plus m x dot theta dot cosine of theta. And now the partial derivative of the Lagrangian with respect to the u coordinate. This u coordinate appears again both in the expression for kinetic and potential energy, so we have to be careful here. But if we do all very carefully, we can obtain the following results: m theta dot square L plus u plus m x dot theta dot cosine of theta minus ku, these terms belong or came from the potential energy, plus mg cosine of theta. Okay, perfect. Then finally the third and final equation of motion, it's read as follows: m u double dot plus m x double dot sine of theta plus m x dot theta dot cosine of theta, and now minus all the terms contained here in this partial derivative with respect to u, minus m L plus u theta dot square minus m x dot theta dot cosine of theta plus ku minus mg cosine of theta, and again all of this is equal to 0. Two terms here cancel out. We can note that this one cancel with this another one, and finally our third and final equation of motions is written as follows: there it is. Perfect. Another rectangle here. Okay, so there we have it, the three equations of motion associated with the three generalized coordinates that we use in order to describe the motion of our mechanical system: x, theta, and u. The equation of motion associated with the x coordinate again is obtained in the first part. If you haven't seen that video, just take a look, and here we have it, our three equations of motion. As I mentioned in the first video, maybe later I will do a video talking about the linear equivalent linear process, how we get rid of these nonlinear terms. If the oscillations are very small, then we can do some very useful approximation, and we can eliminate all the nonlinear terms. But if you know how to code, maybe also I can do a video about how to code in this equation in MATLAB. I have a lot of videos of MATLAB simulations. I can show you how to write a code on MATLAB in order to simulate the motion of this mechanical system. Okay, that's it. That is for now. I hope you like the video. Give a like, subscribe if you like to see more content like this. And if you have any question or comments, just feel free to let me know in the comment section. So that's it for now. Bye bye. Thank you for watching.